Okay. So, we have talked about stationarity and ergodicity, right. What we will now show you is something for means some class of signal, that is probably wide sense stationary signal. We will show you, demonstrate you that some more property of that signal is still predictable. Okay. So, that is something we will try to appreciate today. So, what do we mean by that? Let us say for any signal, all those deterministic signals, so far what we have done, we are trying to see what is happening at the frequency domain, right. So, that was very interesting for us, because with that we were means employing filtering and all other things, which frequency component it has, how to enhance the signal and all those things. Lots of processing and all those things were possible if we visualize the signal in the frequency domain. And whenever we said that frequency domain we want to visualize, I need to do a Fourier transform. So, for Fourier transform the input has to be a deterministic signal. So far this was all good, because I was always dealing with deterministic signal, either a pulse or a sinusoidal or something of that nature. But now we have already declared that most of the signals are not deterministic, because suppose receiver wants to design a filter, he does not know what is coming, he has no idea, it will be a random either a random pulse or a random signal, amplitude modulated, how the envelope is varying, he has no idea. On top of that there will be noise, he has no idea about all these things, okay, because before he receives, how can he know what is there in that signal, right. So, it is random to him, but he wants to design a filter for this, but filter requires frequency domain characteristics, but it is a random signal. So, now what do we do for this? How do we characterize for a signal what will be the spectrum quality of it? But we know that whenever we wish to go to spectrum, we have already devised a strong tool which is called Fourier transform. Right now, because the signal is random, we have no way to characterize it. So, it is very difficult, we cannot do that. So, let us try to see if we can do something. Whenever we are having a random thing, generally how do we measure that or characterize that? It is in average sense. So, whenever we have different kinds of height in a class, if we wish to characterize the height of the class, we say average height of the class. So, similar thing we will try to do over here. So, because it is random process, so that means all the signal that will be coming, that is random. So, we will try to characterize it from the average perspective. Okay. So, we will give some average sense of it. What does that means? So, we assume that these signals are power signal. So, therefore, I will be interested in power spectral density, right. So, what was power spectral density? We have already derived this formula. So, we have said that power spectral density is something like this. Right. So, this is something we have told, that if I have a corresponding xt which is truncated. So, I create a xt where it is nothing but xt into a box function of duration capital T, right. So, it is multiplied by a box function where it is defined from minus t to plus t and rest of the things are 0. So, it is just basically truncated. So, this I can get a corresponding Fourier transform as long as xt is known to me. Okay. So, if xt is a deterministic one, then xtt also will be a deterministic one, and then what I can do? I can take a corresponding xtf, okay, Fourier transform I can do. So, it is this Fourier transform, then divided by t, t tends to infinity. So, that was the definition of my Sxf, but now my xt is a random process. So, what I have to do is, I need to, if I wish to calculate this power spectral density, that must be the average power spectral density. So, therefore, that average power spectral density should be, I should take average of this. So, xtf mod square divided by t, average of that. So, all I have to do is, I have to do the ensemble average of this whole thing. Okay. So, that should characterize in average sense what will be the power spectral density, and I need to see whether this is something I can characterize. Okay. So, that is something we will try to do in this class. Okay. So, let us say I have a particular signal x t whose Fourier transform is this means x t f. So, therefore, I can write the corresponding signal x t t, it should be e to the power minus j 2 pi f t dt minus infinity plus infinity, right. I can write this because this is just the Fourier transform of the truncated signal, as long as I have picked a sample. Okay. So, I am ensembling or ensemble averaging I will do later. So, this is just a picked sample, and then because x t is truncated already, I can write that this is minus t by 2 to plus t by 2 x t e to the power minus j 2 pi f t dt. I can write this because it is truncated. As long as I take the limit from minus t by 2 to plus t by 2 over that t duration, whether I write x t t or x t, it is the same, because within that truncation it is the same thing. It is just beyond this, it is 0 for x t t and it is having some value for x t. Because I am not going beyond that, so I can write this, and this are equivalent, because beyond plus t by 2 this is 0. So, there will be no value. So, this and this are equivalent, I can write this way. Okay. Similarly, I can also define x t minus f, right. So, which will be nothing but minus t by 2 to plus t by 2 x t, this will be just plus e to the power plus j 2 pi f t, because it is minus f. So, minus f minus it will be plus dt. Okay. Now, what is mod x t f whole square? That I can write as x t f into x t minus f. Why? Because we know that x t minus f is complex conjugate of x t f. This is something we have proven already. So, if I just multiply these two, that must be giving me x t f mod square for a real signal, of course. So, I can write these two, and because there are two t integration, I will take two dummy variable t 1 and t 2, right. So, we just do it minus t by 2 to plus t by 2 x t 1 e to the power, let us say j 2 pi f t 1. So, I am just first writing x t minus f d t 1 minus t by 2 to plus t by 2 x t 2 e to the power minus j 2 pi f t 2 d t 2. So, this is this one, this is this one, d t 1 and d t 2. This is just two dummy variable I have taken. It was integrated over t because both of them are t. So, because I will be taking double integral, means I will be representing them as double integral. So, I do not want to confuse those two random, means those two variables. So, because this and this are independent, so I can take that whole integral out. So, from minus t by 2 to plus t by 2, minus t by 2 to plus t by 2, x t 1, x t 2 e to the power minus j 2 pi f t 2 minus t 1 d t 1 d t 2, right. I can write this. Now, I wish to get that x t f average, right, which will be nothing but if I just take divide by t, take a average and take limit t tends to infinity, if I just do that. So, what will happen to this side? It should be average and there should be 1 by t limit t tends to infinity. So, I am just modifying it, right. So, that should be the overall thing. Now, this ensemble average is over these values, right. These are the random values, that is one integral, okay, and that has nothing to do with this t 1 and t 2 integral. So, therefore, I can actually exchange these two integral. Ensemble will be also an integration over this random variable, okay, that x and x at t 1 and x at t 2, okay, which has nothing to do with this other random variable, sorry, other variable of integration, okay. So, therefore, I can take the ensemble average inside, no problem in that, it is just, and the limits are not dependent. So, I can take them inside. So, I can just write this similarly t tends to infinity, this minus 1 by t remains, this remains. So, it is x t 1 into x t 2 average e to the power minus j 2 pi f t2 minus t1 dt1 dt2, right. Now comes the stationarity property. What is this? That is actually the autocorrelation function in ensemble domain, right. So, if the process is at least wide sense stationary, that means the second order should be just a autocorrelation function which depends on the separation of these two. So, I can write this. So, therefore, Sx(f) I can write as limit t tends to infinity 1 by t minus t by 2 to plus t by 2, another integration minus t by 2 to plus t by 2. This I can write as R x t2 minus t1 e to the power minus j 2 pi f t2 minus t1 dt1 dt2, right. I can write this. So, this whole thing now, as long as they are wide sense stationary, this whole thing now becomes a variable of t2 minus t1. So, I can define that as phi t2 minus t1. Okay. So, therefore, the whole process becomes limit t tends to infinity 1 by t minus t by 2 to plus t by 2, again minus t by 2 to plus t by 2 phi t2 minus t1 dt1 dt2, right. So, this is what we have got so far. Now, we will do a trick. So, from this double integral we want to convert it to a single integral, that is something we wish to do. Why we are doing? Because we want to actually this Sx(f) we want to relate it to the autocorrelation function. Okay. So, we have related it somewhat, but we need a little bit more concrete nature of it. Okay. So, let us try to see if we can further simplify it. So, what we wish to do, this t2 minus t1, that should be a variable. So, we define tau as t2 minus t1. Okay. Let us see how the integration variable changes. So, this was my t1 and this is my t2. The overall integration, if you just see this is happening over this box of dt1 dt2, where t1 is varying from minus t by 2 to plus t by 2 and t2 is varying from minus t by 2 to plus t by 2. So, it will be a box of size t cross t, okay. So, which is something like this. Where this is plus t by 2, this is plus t by 2, this is minus t by 2 and this is minus t by 2, right. All right. So, now we need to also define in this plane this particular variable, which is tau equal to t2 minus t1. This is nothing but a straight line of 45-degree slope, okay, because t2 is exactly t1 plus tau, where m is 1, 1 means tan theta should be 1. So, that means it has a 45-degree slope and it cuts at, that is the cutting point at tau. If I take the next line and I increase tau by, this becomes tau plus del tau. So, this must be the equation t2 minus t1 equals to tau plus del tau. So, that is the equation of this line and this line will have equation t2 minus t1 is equal to tau. Okay. So, now we wish to convert the integration over this tau. How do I do that? So, instead of integrating it over, suppose at t1 and t2 I have a box, right, of dt1 and dt2. Instead of that box, if I just do this integration over this strips, okay, and then what will happen? If I just this tau, if I start varying it, so at tau equal to t, it will just be crossing it. That is very clear, because this is t by 2 minus t by 2 minus t by 2. So, at tau equal to t, it will just be touching that. Okay. So, at tau equal to t to tau equal to minus t, if I just keep changing tau, it will just sweep through the entire thing. All I have to do is Because of that, whatever strips will be happening, I need to take the area of that. Over that area I have to do the integration. Okay, so that is all I will have to do. And if this d tau is sufficiently small, why I am doing this? Because I had a inside variable which is phi t2 minus t1, which is already phi tau. So, if del tau is sufficiently small, over that strip phi tau will not be changing. So, that is why I can do this integration. Okay. Just the area dt1 dt2 has to be changed to this particular area. As long as I am doing that, it should be converted to a single integral, right. So, I have to then evaluate the area, okay, because I have already seen the limit of t tau that goes from plus t minus t to plus t. Okay. So, I just have to get the area. So, for calculating that area, I need to find out this length, okay, because the angle I know already. So, immediately I will be getting this value. Okay. So, this is something I can always do. So, basically if I just draw it little bit bigger, so let us say this is actually t2 minus t1 equals to tau, right. So, what is this point? At this point my t2 is t by 2. So, t2 is t by 2. What will be t1? That must be this. Okay. So, t1 is actually t2 minus tau and t2 is t by 2. So, t by 2 minus tau. So, that is this value. I need this. So, that must be, because it is already in negative. So, it must be this value minus this value, that will be a bigger negative. So, they will give me the distance. So, this value is already t2 minus tau. So, if I wish to get this, that must be t by 2 minus tau minus this value. What is the value over here? Minus t by 2. So, minus of minus t by 2, that gives me t minus tau. So, this particular value is t minus tau. If this is theta, then what should be this? This should be t minus tau divided by cos theta, right. So, I have got one arm of this. I need to also get another arm of this, sorry, this particular thing. This triangles will be very small, it can be cancelled out. Okay. So, that will be inconsequential, because that will be del tau square. So, I can neglect that as long as del tau is small. So, I just need to get this box. Okay. So, if now you can see basically this is del tau, right, because over here that was the increment tau to tau plus del tau. So, this must be del tau. What is this? This is already theta, that particular small angle between this line and this line, that is theta. Okay. So, immediately that should be del tau cos theta. So, this multiplied by del tau cos theta must be giving me this whole area, this strip area. Cos theta gets cancelled. So, that must be t minus tau into del tau. Okay. That is actually the strip area. And whenever we do integration, so at every value of this tau, this area has to be considered. Okay. So, therefore, the integration should be, okay, I should also specify another thing, that this was true when I was in the positive half of tau. If I go to the negative half of tau, you will be able to similarly prove that this should be t plus tau del tau. This something can be easily proven, similar way. Okay. So, basically I can write that this should be t minus mod tau into del tau, right. I can write this area as this. Once this is the case, now I go back to my calculation. So, Sxf was actually limit, I will write it one more time, 1 by t minus t by 2 to plus t by 2, again minus t by 2 to plus t by 2, phi t2 minus t1 dt1 dt2. This integration now can be converted, limit t tends to infinity 1 by t. This becomes a single integral now over tau. So, the area for that integration is t minus mod tau, sorry, del tau, that becomes dt, d tau, and this is already phi tau integration, and the limit goes from minus t to plus t, that is what we have seen. So, minus t to plus t, right. So, this is the overall integration, limit t tends to infinity. I take the t inside because that has nothing to do with the integration. So, if I just take that, what will happen, because it goes to infinity. So, I can even write that to be infinity. So, basically I can take this limit, I might write this to minus infinity to plus infinity phi tau, and now this will be 1 minus mod tau by t. Of course, here that limit t tends to infinity should be there, okay, d tau. Now, this is something where we have to specify that this, as t goes to infinity, probably this might be cancelled out, but we should be very careful about that. We have to say this thing, that as long as this particular integration phi tau mod tau d tau is bounded, most of the signal that we will be considering, this will be bounded. Once this is bounded, divided by t, okay, and t tends to infinity, that goes to 0. So, therefore, I will be, this term gets cancelled, I will be left with minus infinity to plus infinity phi tau d tau, which is nothing but minus infinity plus infinity. Now, replace phi tau, it was actually r x tau e to the power minus j 2 pi f tau d tau. Can you identify this form? This is nothing but the Fourier transform of r x tau. That is a fundamental theorem of random process, that whenever we have a random process which is characterized as either wide sense stationary or stationary, I will be having a r x tau calculated or t 2 minus t 1 calculated. If I know that, I can always relate, means do a Fourier transform of that. So, that means r x tau, if I just do Fourier transform, I get back my S x f, which is defined in average way. So, this is the average power spectral density, because we told for a random thing, random signal, I can never calculate the actual power spectral density, because every signal will have its own power spectral density, but what we can characterize is the average power spectral density. And we have got now a very strong formula where it is characterized that if I know that signal is stationary, it would not have happened if the signal was not stationary, because then the whole process will not be proven. If the signal is stationary or at least wide sense stationary, that means up to second order it is stationary. If that happens, then the autocorrelation function, if I can somehow evaluate, you just take a Fourier transform, you get the average power spectral density. And once you get the average power spectral density, now you can, even though that was a random process, you have the average power spectral density, with that you can design the system. Okay, that is the advantage you get, otherwise you could not have done this. So, this is the famous Wiener-Khinchin theorem. So, that is the WK theorem we all know about. So, this is that fundamental property of a random process. It says that as long as, and that is why we were saying so much of things about a stationary or wide sense stationary random process, because as long as a random process is stationary or wide sense stationary, we know that we can always derive its average power spectral density, which will be used for characterizing the signal. Okay. So, that means if I have a random signal, I should not now worry, I just have to test whether it is at least wide sense stationary. That means second order statistics is still stationary. As long as I know that, I know I still have a means to go to the spectrum. Earlier I was little bit afraid that if the signal is random, I have no way to go to the spectrum, I do not know how to exploit the spectral property of the system, of the signals. Okay. But now with this strong relationship, I know that as long as I can evaluate somehow the autocorrelation function, I will be able to characterize the corresponding average spectrum. Okay. So, this is a fundamental theorem, and this will be used. Now, let us, after knowing this, let us talk about something which is very fundamental to noise analysis. Let us try to see what is noise. So, noise is something which is completely random to us. That means, if I observe something, at the next time I do not know what will be happening. That is why we call that noise, okay, because that is completely random, and therefore, in the next time instance, even though it is infinitesimally small, just at t I observe some sample value, even at t plus delta t, let us say over here, even if delta t tends to 0, I have no way to say where that will be, that can take any random value. Okay. This particular process we characterize as noise. Okay. So, that is to our mind that is probably the noise. Okay. You will see that has a special characteristics, but if that is the noise, then what is the, let us try to ask, because if this is noise, this is a random process, I need to first just try to understand what will be the corresponding autocorrelation function. Okay. I can immediately see, because at this time seeing something, I am not able to, at the next time what will be happening, I am not able to tell, that means it is completely uncorrelated. So, time you just progress little bit, I must not get any correlation. So, the correlation value should be 0. So, what I can say, but signal with itself, it has full correlation, it will be very high correlation, because that I know exactly that signal it will be. Only thing is that I just shift the time even a little bit, I know that there will be no correlation, absolutely 0 correlation. So, if this is the case, then the autocorrelation function should ideally look like a delta function, right. So, that is noise for us. Whenever we characterize noise, we say it does not have any correlation to next time instance, and immediately single function comes to our mind, that is the delta function with some strength of that delta, let us say that is eta. Okay. So, with that in mind, immediately what will be the corresponding Fourier transform? That should be the power spectral density of it. We know delta Fourier transform is Tc. So, this is the power of strength theta. So, this is actually for noise, this is the power spectral density. What does this say? That it has equivalent component at every frequency, or equivalent amplitude or power at every frequency, and that is why probably we say it is white noise. That means all equivalently all frequency components are present, and it will be white noise because it is the most random noise that we know, which has no correlation whatsoever. Even if I know some means observe some sample value over here at a particular instance of time, in the next time instance I cannot predict anything about it. Okay. So, whenever the signal is like that, I have a autocorrelation function which is delta. So, immediately you can see why this particular thing is so important, is that I have a sense of creating autocorrelation function from the description of the noise that I have in mind, the most random noise that I know, and then immediately from there I know the spectral property of that noise because of Wiener-Khinchin theorem. So, that is the strength of Wiener-Khinchin theorem. So, once I know that random process, even though the signal can be anything, see the signal can be of any nature, I do not even know. Even though the signal is like this, I have a very nice spectral property of it. That is the fundamental postulate over here. So, immediately I know the noise characteristics, and this is actually called the white noise. Okay. So, once we have that spectral property of noise, now we can actually start dealing with this noise, that what this noise will do to my signal and how I should restrict this noise. So, immediately you know that the filtering is a big thing in noise, means combating noise. Wherever your signal is, you just filter that portion out, because rest of the noise will be immediately suppressed. If you do not apply filtering, see, even if you do not have any other signal, still you are actually taking lot of noise to the receiver, and that will contaminate your signal. Whereas, if you just suppress it, lot of power, signal power will relate signal power to this autocorrelation as well as the spectral property of it. but you will see that lot of extra power, noise power, which is contaminating the signal, are unnecessarily coming to your receiver. So, that is why filter has a big role whenever you are combating noise. So, what we will do next, we will try to appreciate all these things to see how noise analysis can be dealt with in a communication system or particularly analog communication system. Okay. Thank you.